Okay, so let's get right into it. We're tackling a really fundamental question today. A listener sent in some sources asking something that I think is on a lot of people's minds.
Oh, yeah.
How can scientists be so, intensely confident that something exists when it's totally invisible, something they can't see, can't touch, can't measure?
Right. It's a perfect mission for a deep dive because on the surface, it sounds like pure speculation.
Exactly.
But the evidence is, well, it's overwhelming. We're talking about dark matter, which is, frankly, most of reality.
And that's the core idea in these sources, right? That everything we see, every star, every planet, the dust, even us, it's just a tiny, tiny
It's
fraction.
just the crumbs.
Yeah, the cosmic crumbs. And the vast, 85% of all the mass in the universe is just missing,
Yeah.
unaccounted for.
So our mission today is to dive into the three big gravitational proofs that tell us dark matter has to exist,
Hmm.
and then try to understand why this cosmic ghost is so stubborn, why it's so hard to find.
I like that. A cosmic ghost. The sources used a great analogy. It's like feeling the wind shift or hearing footsteps behind you. You know something is there, even if you can't see it.
There's it exactly.
Yeah.
We're not seeing the thing itself, we're seeing its effect. And in this case, it's a profound gravitational effect.
It's not about belief. It's about observation. The universe is telling us its structure just doesn't add up without it.
That's the core of it. If you take our best model of gravity, Einstein's general relativity, and you apply it to a galaxy, the math just completely falls apart.
Unless...
Unless you add in this huge chunk of invisible mass.
Okay, so let's start there. The hard evidence. The first pillar of proof. This is where it all started, right? Galactic rotation speed.
This is the definitive smoking gun. So when you look at a spiral galaxy, you expect it to spin kind of like our solar system.
Okay, so things in the middle move fast and things on the outer edges move slower.
Precisely. The mass is concentrated in the center, so things farther out should feel less gravity and slow way, way down. That's just basic Newtonian mechanics.
But that's not what we see, is it?
Not at all. What scientists like Verhoeven found were these flat rotation curves,
Meaning?
meaning the stars way out on the fringes, where there's hardly any visible gas or light, are moving just as fast as the stars packed into the core.
Wait, if they're moving that fast but there isn't enough visible stuff to hold on to them,
Yeah.
shouldn't they just...
Fly off into space.
Yes.
They should be flung out into the void.
Exactly. If we only count the visible matter, the galaxy would tear itself apart. It wouldn't be stable. So the only way for that galaxy to hold together is if there's a massive invisible halo of something providing the extra gravity,
The anchors.
the gravitational anchor. And we're not talking about a small correction here.
No.
Not at all. The data suggests for a typical galaxy, something like 90% of its mass has to be invisible.
90%.
It's a 10-to-1 ratio. This isn't a rounding error. It's a fundamental crisis in our inventory of the cosmos. That pull, that's dark matter.
Okay, that's a huge one.
Yeah.
Let's move to the second proof. This one involves the bending of space-time itself, gravitational lensing. Right, so we know from Einstein that anything with mass warps the fabric of space-time.
And light has to follow those curves.
Exactly. So when we look at massive galaxy clusters, they act like giant cosmic magnifying glasses. They're so heavy they actually bend and distort the light from galaxies that are way behind them.
But the weird part is when the bending doesn't match the stuff we can see.
That's the key. You calculate the total mass from all the stars, all the hot gas you can see in the cluster, and it only accounts for a fraction of the lensing effect we observe.
So what does that mean?
It means light is bending around places where there is nothing. No visible mass.
You're seeing the gravitational effect, the curved light, but you point a telescope there and it's just empty space.
It's a mass ghost. The amount of distortion requires this huge spherical bulk of matter that's completely invisible.
The sources mention something called the bullet cluster.
Ah, yes. That's the knockout punch for this. It's two galaxy clusters that collided and passed through each other. The normal matter, the hot gas, smashed into itself and slowed down in the middle. But the gravitational lensing shows that the bulk of the mass, the dark matter, just passed right through without slowing down at all.
So you can literally see the visible matter in one place and the gravitational center of mass in another. They're physically separated.
Exactly. It shows that whatever this stuff is, it doesn't interact with normal matter or even with itself except through gravity. It moves the whole thing from being a calculation problem to a physical reality.
Oh, wow. Okay. Proof 3. This takes us way back. The cosmic microwave background. The sources called it the Big Bang fingerprint.
Yeah, the CMB. It's the oldest light in the universe. The leftover heat from about 380,000 years after the Big Bang.
And it has these tiny little temperature variations in it.
Right. And those tiny variations are the seeds of everything. They're the little dense spots that eventually grew into all the galaxies and clusters we see today.
And the problem is time.
The problem is time. When you run the simulations with only the visible matter we know about, there just wasn't enough time for gravity to pull that matter together to form the structures we see in that ancient light.
Why not?
Because normal matter gets pushed around by light and radiation pressure, it would have stayed too hot and too spread out for too long. It couldn't clump up fast enough.
So how does dark matter solve that?
It provides the scaffolding. Since dark matter ignores light completely, it could start clumping together much, much earlier. It formed these dense gravitational pockets, or wells.
And then the normal matter just fell into them later.
It fell into these pre-existing dark matter structures. It gave structure formation a massive head start. Without it, the universe would look totally different. It might not have even formed galaxies like ours.
So we have galactic motion, late bending, and the structure of the early universe, all three pointing to the exact same thing.
3 wildly different methods, all demanding the same unseen substance. It's pretty robust. But now we get to the pivot, the big question. If the evidence is so strong, why can't we find a single particle of it?
Right. This is where I have to play the skeptic for the listener. I mean, if 85% of reality is this invisible stuff, isn't it also possible that our theory of gravity is just wrong, or at least incomplete?
That is a critical question. And there are theories like modified Newtonian dynamics, or MOND, that try to do just that, change the laws of gravity instead of adding new matter.
So why don't those work?
Well, they sort of work for galactic rotation,
Mm.
but they fail spectacularly when you try to explain gravitational lensing, especially the bullet cluster.
Ah, because the gravity's in a different place than the matter.
Exactly. MOND can't explain that, so the evidence for a physical substance is much, much stronger than the evidence for modifying gravity. We're sort of forced to conclude this stuff is real.
Okay, so if it's real, let's talk about its properties. Why can't our giant telescopes or our super sensitive detectors find any of it?
It all comes down to one thing. Dark matter pretty much only interacts with the universe through gravity. That's it.
And we detect almost everything else using light.
Everything. We use the electromagnetic force. Light, radio waves, X-rays. It's all photons. Dark matter is completely immune to photons.
So it doesn't absorb light, it doesn't reflect it, it doesn't emit it.
Nothing. It's totally transparent, which means every single instrument we've ever built to look at the universe is basically blind to it.
That's worse. What a challenge. It's not electric, not magnetic. It doesn't use the strong or weak nuclear forces that hold atoms together.
Its non-participation in 3 of the 4 fundamental forces is why it's so hard to catch. If it interacted even a tiny bit through the weak force, like a neutrino does, we probably would have found it by now.
But the theories, the main candidates for what it could be, WIMPs is from, right,
Yeah.
weakly interacting massive particles, that name implies there is some interaction.
A very, very weak one. That's the hope, that there's some tiny, incredibly rare interaction with normal matter.
Yeah.
And that's why the search for it is so extreme.
You're talking about an interaction that might happen, what, once a year in a giant tank of detector material.
If we're lucky, it's right at the absolute edge of what we can possibly measure.
Which brings us to the scale of this. If this stuff is 85% of everything, it means we are just living on cosmic leftovers.
The contrast is just staggering.
Yeah.
We built all of science, chemistry, biology, astrophysics, studying the 15% we thought was the whole story. The real structural ingredient of the cosmos is, to us, totally inert.
So the real universe is basically hidden from us. And it's everywhere, not just in distant galaxies.
It's everywhere. We're swimming in a vast, diffuse sea of dark matter particles right now as the Milky Way moves through its own halo.
That's a wild thought. So how are scientists trying to catch one? What do these searches actually look like?
They're building these incredible experiments deep, deep underground.
Why underground?
To get away from all the noise. Cosmic rays from space, natural radioactivity from the rocks. All of that would just swamp the detector. You need to shield it.
So they go down into old mines or under mountains.
Exactly. They build these huge, pristine tanks filled with ultra-pure liquid noble gases like xenon, and they wait.
Waiting for what?
Waiting for a single dark matter particle, one that has passed through the entire Earth, to just happen to bump into one of those xenon nuclei.
And that would cause a tiny flash of light.
A minuscule flash. The goal is literally to catch one atom getting knocked by a dark matter particle. Just once.
And the sources say that so far, after all these years and millions of dollars, nothing. Without benefit until now was the phrase.
That's right. The silence is deafening. It's telling us that either our main theory about what it is, the wimpy model, is wrong, or this particle is even more ghostly, even more weakly interacting than we ever imagined.
It's such a paradox. We have three incredibly strong independent lines of evidence telling us this stuff makes up most of the universe, that it dictates everything, and yet it just slips through our fingers every time.
It forces us to reconsider what matter even is. I mean, understanding it isn't just some niche physics problem, it's fundamental to knowing the history and the ultimate fate of our universe.
And this brings it all home. The final, slightly chilling thought that really stuck with me from the sources
hmm
is that because it's everywhere and passes through everything, there are trillions of dark matter particles streaming through you, the listener, right now, passing through your body, the device you're listening on, the floor, every single second.
And you'll never, ever feel a thing. It's the ultimate invisible reality.
Oh, wow.
And it leaves you with a final provocative thought, doesn't it? If 85% of the universe's mass is made of something that only interacts through gravity, the weakest force we know, what else might be out there? What other fundamental forces or particles might we be missing just because they're too subtle or too stubborn for our current tools to detect? Maybe dark matter isn't the end of the mystery. Maybe it's just the beginning.